Welcome to the Jansen Potash Project in Saskatchewan, Canada, located on Treaty 4 territory and homeland of the Métis. The Jansen Project has the potential to be the largest potash mine in the world and sits on one of the best undeveloped resources globally. Come with us as we tour around the current site, completed works to date, and show you the built-in competitive advantages that will shape what Jansen's Stage 1 will look like. Work completed on-site to date positions Jansen well for the execution phase and provides a solid platform to deliver Stage 1, guiding it on a trajectory to be the mine of the future.
The work done to date is life of mine infrastructure. That is the vehicle to help us bring potash ore to the surface safely and efficiently.
Let's take a closer look at what is happening in and around the headframes. Between the two shafts, you can see the freeze plant, which was critical to shaft development and used to artificially freeze the ground around the shafts down to 700 meters below surface. This is around 40% deeper than older mines. This helped the team control underground aquifers and reduce the risk of any water issues that may have occurred underground. For example, freezing any carbonite zones rather than the traditional grouting to seal them off. We are also using the most advanced instrumentation to monitor and predict stress on the liner and managing the impact of lower temperatures on the frozen ground.
The freeze plant has capacity to freeze 30 hockey rinks.
The service shaft headframe is one of the tallest structures in Saskatchewan and stands at 97 meters tall. The headframes on both shafts, along with the hoist houses on the east and west sides of the headframe, help support the ropes used by the hoist system. This is the construction hoist house, where the hoists are operated and maintained. Since these are the machines that move materials and people up and down in the shafts, the hoist system is operated with safety-critical controls in place. A revolutionary shaft boring road header, or SBR, was used to excavate both shafts. This method helped remove risks associated with regular drill and blast operations in shaft sinking. Apart from sinking the shaft, the SBR also assisted with primary liner install. A deck was set up for applying mesh, bolting, and concrete.
Something to note is that the SBR had an arm specifically for the Blairmore aquifer, a ring erector which was used to install tubbing segments through the Blairmore in the shafts. It was a mechanical arm that was remote controlled by an operator who would pick up a piece of the ring and place it into position for it to be bolted to the shaft wall.
Shaft bottom was reached in August 2018. These were the first mechanically excavated shafts in the world. We are now at the Galloway, a work platform comprised of 7 decks. Each deck performs a critical task that contributes to the overall construction of the final liner. The Galloway is lowered on ropes to the shaft bottom, approximately 1,000 meters below ground, and lining occurs from the bottom up. Final liner material is made up of concrete and a watertight welded steel liner. Back on the surface, you can see both the warm and cold storage warehouses, which are both required due to the extreme temperature ranges we experience. The batch plant is also on the north side, which is delivering concrete 24 hours a day for shaft construction and produces 30,000 cubic meters of concrete per year, a number that will increase as Jansen Stage 1 enters the construction phase.
30,000 cubic meters is enough concrete to line just over 3,300 swimming pools.
The concrete mix produces concrete that is 3 times stronger than standard strength, which is critical for shaft integrity. The project has been significantly de-risked through the construction to date, even under challenging times such as the COVID-19 pandemic. Our risk management is underpinned by safety-critical systems and a workplace culture that values a safe-to-speak-up approach. Now, let's see what the site will look like in Stage 1. 2 shafts have been excavated and permanently lined. However, for Jansen Stage 1, only the service shaft is required. The 2 skips located in the service shaft will hoist ore to the surface, provide ventilation, and transport personnel and equipment.
Ore will be hoisted using 2 50-ton skips, and the mine shafts will be extended to below potash zone level of approximately 1,000 meters. The shaft's pillar area will contain life of mine facilities, including equipment assembly, maintenance shops, and overhaul.
Jansen Stage 1 will develop 2 mining districts. The East District will be developed first, followed by the North District. Both districts proceed to establish production panels for the fleet of 4 mining systems. Each production panel consists of rooms that are approximately 12 by 5 meters and up to 1.8 kilometers long. There are up to 60 rooms in each panel, and mining retreats toward development roadways over several years. Rooms are excavated with the Sandvik borer miner and extendable belt mining system. The larger size of the borers gives us a competitive advantage, as 4 mining systems produce equivalent of 10 to 14 standard systems in other mines. The higher capacity systems mean fewer active mining phases, approximately 60% less fleet, and an approximately 15% operating cost saving. The borer excavates the full height of the potash seam and completes the room in 2 passes. This provides higher throughput and delivers better productivity than traditional low-profile borers used by competitors. Traditional borers cannot reach full seam height and require a 4-pass benching method. The larger borers Jansen Stage 1 will use are capable of producing raw ore at 2.7 million tons per annum, more than double the rate of low-profile borers used by competitors. From the production rooms, raw ore is transported through a network of conveyors sized for optimum capacity. In Stage 1, there will be approximately 23 kilometers of conveyors underground, extending to over 100 kilometers in Stages 2 and 3. Underground storage provides a buffer from the mining districts to maintain consistent feed to the hoist. This is the 5,000-ton bin for Stage 1. This large bin feeds into a surge bin for optimal loading of the shaft skips. The skips are loaded at the station level via 50-ton flasks. The skips travel at 18 meters per second to the surface and unload within the head frame onto the first surface conveyor. Enclosed belt conveyors transfer raw ore from the shaft. A tripper conveyor builds an ore stock profile to a uniform profile for reclaiming. Raw ore is reclaimed using a fully automated bucket ore reclaimer, enabling remote operations.
The crushing building represents the final step of the raw ore handling. Jansen's crushing building is located away from the mill to minimize noise and dust.
The wet processing area separates the potash from salt and insoluble tailings using the latest in proven column flotation technology, and separates coarse and fine flotation circuits to maximize recovery. In the dry processing area, potash product coming from wet processing is centrifuged and dried. Screens separate the standard-sized product from the oversized and fine material, which is then compacted to produce granular product.
The dry process also uses discrete, parallel processing lines, which provides the ability to flex the output of the 2 products to meet seasonal marketing requirements.
The finished product is transferred via belt conveyor to the product storage building, where it is stored in stacked stockpiles prior to train loading. Product is reclaimed from the storage building at an industry-leading rate using a fully automated reclaim system. The potash is then screened and loaded into rail cars. Hazards associated with manual train loading operations have been eliminated using a fully automated continuous loading design, which removes the need for any direct interactions between personnel and rail cars. The system includes remote train control and automated wayside robots to open and close the rail car hatchets. The train loadout will be capable of loading a 177-car unit train in less than 6 hours, a faster rate than existing operations. An integrated operations center will be located in Saskatoon and will serve as a combined office and control room for the Jansen mine and port.
We're so very proud of the people in Team Jansen and everything we've accomplished on the project so far. We do look forward to evolving our approach to enhance that project construction and carry those improvements into the operating phase.